Hello everyone, my name is Loïc Jean-Marie Guizouin and I'm a PhD student in the University of Nice Côte d'Azur in I3S laboratory. With my supervisors, Etienne Loz and Cinta Di Giusto, we did the work I'm going to present to you now. To give a little bit of context first, we need to talk about model checking. So in general, model checking is a way to analyze software to know whether it is conform to some specifications. So the typical way to do that is to compute a model of the software and check this model against some specification. Computation of the model can be done with different approaches, and I don't want to dive into this aspect now. So only thing I want to point out is that usually we want the model to be an over-approximation of the potential bugs of the software. That is, if a bug is present in the software, we want it to be present in the model, but we do not require the converse property, because whenever we'll find a bug in the model, we can still go back to the software to see if the wrong behavior was only existing in the model or also in the original software. What we are going to focus on today is verification of communication protocols. So our model will be communicating automata. I will start by showing you how this model works with an example. So the system you see here represents a simple protocol involving a client, a server, and a database logging activity. In communicating automata, we represent each participant of the communication protocol with an automaton. So the transitions here are labeled with actions, so either reception or send actions. And to explain this representation, the bang means we are dealing with a send action, and the question mark, we are dealing with a reception. If we take this action, for example, it means sending message res to buffer C, and this action means receive message rec from buffer S. So the buffer I just mentioned are FIFO queues, and in this example, each automaton has one from which it can receive its messages. So to keep defining key concepts about communicating automata, we need to talk about configurations. So a configuration is basically the state of a run of the protocol at a given time. A bit more formally, it's the vector of states of each automaton and the content of all the buffers involved. We illustrated on the example we have here the initial configuration of the system, and you can see the current state for each automaton is highlighted, and we represented the FIFO buffer, which are empty. I'll show you now how an execution happens with an animation. So the first transition we execute is a send action, highlighted in orange. So it means we are sending message rec to buffer S. So the message is sent to the server's buffer, as we can see in the server's buffer underneath the server's automaton, and the client's current state changed. So the next action is a reception of the request by the server. So yes, because the message name rec stood for request. So the message is consumed from the server's buffer, and the server changes of state. Then we'll execute this transition, so the server sends a result to the client. And if we stop there, we reached a new configuration, as mentioned here, so server in state 2, client in state 1, and database in state 0, with res in client's queue, and all of the queues empty. So what I just showed you was basically an execution, and we can write it with a trace of the successive actions we executed. So here it was sending rec to S, then receiving rec from S, and finally sending res to C. So now that we saw a little bit how this model works, we can ask ourselves how it will help us to verify communication protocols. So what are the properties we want to be able to check? Here are some examples of questions we can ask about a system of communicating automata. So the first one is, if we can describe the configuration and say, reaching this would be an error, we want to be able to say whether or not, by executing the protocol, we will be able to reach these configurations. Another question we can ask is there any configuration of a certain kind that is reachable? For example, if we define a deadlock configuration as a configuration in which all the participants are waiting for a message, and therefore none of them is sending the message, is there at least one such configuration reachable? And for a slightly different question, we could want to be able to tell if it will always be possible at any step of any execution to keep doing something to do one more step. Said differently, from any reachable configuration, will it be always possible to execute at least one action? It turns out that in general, those verification problems are undecidable. In fact, communicating automata are Turing powerful. If we imagine a system with two participants, one of them simply receiving messages in its buffer and writing them back to the other's buffer, we have an automaton that can read and write in the same FIFO buffer. This allows to simulate the tape of a Turing machine if we can think of it as a circular tape that can grow unboundedly, as you can see represented on the image on the right. So the issue we have here is that being able to tell if a given configuration is reachable on this system simulating a Turing machine would mean being able to tell if a program running on the Turing machine would halt. And we all know that this is undecidable. From this intuition follows that all the verification problems we mentioned in the previous slide are undecidable. So from this arises a field of research that is defining classes, kind of like families of systems, in which the problems become decidable, and if possible, in reasonable time. So the goal is for those classes to be as restrictive as necessary to allow decidability of verification, and as general as possible to allow representation of the greatest amount of protocols. So to go back with our initial diagram, where these classes will come into play are the two orange sections. So in the model checker, we'll use the semantic of a class for which we know the problems are decidable. So at least we know that the verification will terminate. So the issue is that here we might get an under approximation of the presence of bugs in the software. However, this under approximation can be exact, and we may want to be able to decide whether this is the case or not. And in any case, even if the under approximation is not exact, it can still help us finding bugs. It just can't prove absence of bugs, but it can still be useful to fix some bugs in a particular software. So I talked about defining a family of systems. An example of such a class of system is half-duplex systems, as introduced by Cece and Finkel. This class is defined for systems with two participants, with one buffer in each direction between them. And the restriction is that both those buffers cannot contain messages at the same time. That is, if one channel contains pending messages, the other one must be empty. We can visually get an intuition on why this restriction prevents the construction of the Turing machine we did earlier. Let's say the automaton on the right is the one simply repeating the messages in its input buffer to the buffer of the other automaton. Now, the repeating automaton, so this one I just talked about, would have to start by reading all the messages before sending the first one. Because remember, we only allow one buffer to contain messages. So when the repeating automaton starts sending messages, the only memory it has is its state. And we cannot mimic a Turing machine state with that. This is only an intuition, but from that follows that reachability of a configuration is decidable in this class, and many verification problems are as well. And to only mention the one I previously presented, reachability of a deadlock configuration is decidable. Another interesting property is the decidability of the membership of this class. That's what will help us to know whether we are getting an under approximation or not when using this semantic to model check a system. So this class is quite interesting. The only limitation it suffers from is that it is only defined for two participants protocol. So what we wanted to do was to try and generalize this class, and more precisely these properties, to a class of systems with any number of participants. And so we arrived to our contribution. We introduced a new class, the greedy systems. For systems in this class, all the executions can be reordered so that send actions are immediately followed by their reception. Intuitively, it means that no message need to wait more than one execution step in a buffer. Messages can always be consumed right away after they are sent, hence the name greedy. The system we showed earlier is greedy, so I'm going to show you what reordering executions means with an example. So let's take one of the executions of the system. It starts just as the one I showed before, and it keeps going until the last reception, which makes this execution not greedy anymore. Indeed, we see that this message ACK-S is sent and is not received right away. There is this message log-C sent between the send and the reception of ACK-S. But what we can notice is that those two transitions, the reception of ACK and the send of log, are not dependent on each other. They happen on different automaton and involve different buffers. So there is nothing preventing them from being inverted in the execution. And if we do so, the execution we obtain is greedy. We can see that now we have all the send actions immediately followed by their reception. So we saw an example of a greedy system. I wanted to show you how does a system that is not greedy looks. And as you can see on the example here, if the first transition we execute is a send, the next one has to be the other send. If we consider an execution in which both receptions happen as well, there is no way we will never be able to organize this execution such that both receptions happen right after their respective send. This clarity is quite closely related to another one introduced by Boisjani. In fact, we can see greedy systems as a specialization of k-synchronizable systems with k equals 1. Now that we know how this class works, let's see what decidability properties we have. So one of the main points our results rely on is that we can show that the set of greedy executions of a system is regular. That is, if we consider the traces of executions as words, the greedy executions that are actually possible on a given system can be recognized by a standard automaton. However, the set of reachable configuration is not regular, but the intersection of a regular set of configurations and the set of reachable configuration for a greedy system is regular. The idea is that among a regular set of configurations, finding those reachable through a regular set of executions is possible with an automaton. Remember that each execution of a greedy system can be seen as a greedy execution. So to sum up, we show that reachability of a regular set of configuration is decidable for greedy systems. So what is a regular set of configurations, you might ask? Well, to begin with, one configuration is a regular set of configurations. So we know reachability of a configuration is decidable for greedy systems. The set of deadlock configurations for a system is regular as well. So we can also prove that finding whether there is a deadlock configuration in the system is decidable, again, for greedy systems. The last one is a bit trickier, but to answer the third example of verification problems, if we want to know whether we will always be able to execute an action from any reachable configuration, we can check whether we can reach a configuration in which we cannot execute an action. It turns out that the set of configurations where we cannot execute any action is regular. So this third verification problem is decidable as well for greedy systems. Another important decidability result is that membership of the class of greedy systems is decidable. To show you how we prove that, I need to introduce what we call a borderline violation. So a borderline violation is an execution that cannot be reordered to be greedy. Its other specificity is that it is composed by a greedy prefix, and just the last action, a reception, makes it not greedy. This last action is a reception of a message sent earlier in the execution. We showed that the set of these borderline violations is regular, and we also showed that if a system is not greedy, it admits at least one borderline violation. And as we remember, the set of greedy execution is regular. If we compute the intersection between the set of borderline violations, which is a regular set, and the set of greedy executions of the system, adding a reception to them, we can answer to the membership problem. If the intersection is not empty, then there is a borderline violation executable, and therefore the system is not greedy. If the intersection is empty, there are no borderline violation executable, and therefore the system is greedy. Our goal was to generalize the half-duplex notion, so we also introduced another class of systems, a mailbox half-duplex system. We define them a bit like we did for greedy systems. So we begin by defining a half-duplex execution, which is an execution where no message is sent by a participant before receiving all the pending messages in its queue. From this we can define a half-duplex system, which is a system for which all executions can be reordered as half-duplex executions. For two participants, our definition is identical to the one of binary half-duplex systems we presented earlier. And we showed that systems in this class, so the Matebox half-duplex systems, are greedy. So we can say that this class is a good generalization of their work to system of any number of participants. So to sum up, we introduced two classes, the class of greedy systems, for which all regular verification problems are decidable, and Matebox half-duplex systems, which benefit from the same decidability results and generalize the binary half-duplex systems of Seyss-Finkel. For future work, we are working on an implementation of the verification of the greedy systems, and we plan on looking into the links between greedy systems and multi-party session types, which are a different model to represent communication protocols. So thank you very much for listening to this presentation.